Welcome back, guys. I hope you're all doing fine. So, as we have completed the resonance, which is the basic for our organic chemistry, we'll start with the types of organic compound in this video, and we'll basically talk about aromaticity, anti-aromaticity, and non-aromaticity, and we are going to do a lot of questions on them. That is why I've already prepared the notes, so we can start directly on our question section. Yeah, let's get started. So, firstly, we'll talk about types of organic compounds. So organic compounds are basically divided into two types. First is your aliphatic compound, second is your cyclic compound. Cyclic compounds are mainly your closed or ring type compound, and aliphatic compounds are your open chain compounds. The cyclic compound are further divided into two as homocyclic and heterocyclic. Homocyclic compound, in the cycle you will only see carbon atoms. As you can see right here, there are only carbon atom present in the cycle. Oxygen is present but outside of cycle, right? Whereas in heterocyclic there will be some other atoms such as oxygen, nitrogen, or sulfur in between our cycle or our ring. And our homocyclic compound are further divided into aromatic and alicyclic compound. Aromatic compound, we are going to discuss about them very soon, and alicyclic compound are the compound which have like I'll just give you an example, which are cyclic compound but aliphatic cyclic compound. Okay, so in a way they are like this. As we can see, three triangle we can see that CH2 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 just combined in a way. Okay, so we'll move on to aromaticity. So for aromatic compound, a compound need to be aromatic. They need to follow, there are certain rules or conditions that it should follow, which are: firstly, it should cyclic, as we talked about earlier. Secondly, the structure should be planar, and by planar I mean all the atom in the ring should be sp2 hybridized, neither sp nor sp3. Okay, only sp2 hybridized. And the conjugation, it should be conjugated, as always conjugated for resonance. As what do conjugation mean? It should have alternate single and double bonds, right? And for aromatic compound especially, the number of pi electrons should be, and what will count in pi electrons is lone pair electron, negative charge that we talked about in resonance. Okay, and pi electron itself. So number of pi electrons should be in this 4n plus 2. So I have derived that in the form of 2, 6, 10, 14. If you see any of these numbers of carbon compound in there, then yeah, pi electron, then yeah, it is your aromatic compound. For anti-aromatic, the first three conditions are same, just the final condition changes, that it should have 4 and pi electrons. So the electrons must be in multiple of 4, 8, 12, 16. Okay, and then non-aromatic compound are basically compound which are acyclic, or either they must have, if a compound or cyclic compound or any other compound have one sp3 hybridized, which is not planar, right? One sp3 hybridized carbon, then it will be non-aromatic. And as far as the stability goes, aromatic compounds are most stable, then non-aromatic and anti-aromatic. Now you'll think anti-aromatic also follow, this is also known as Huckel's rule. Okay, anti-aromatic also follow Huckel's rule. Then why so that anti-aromatic are not stable and non-aromatic are more stable than that? This is the Huckel rule for anti-aromatic, and this is for aromatic. And so the reason of this is aromatic has 2 electrons in their bonding molecular orbital. So it is something related to molecular orbital theory, and whereas even non-aromatic have in their bonding molecular orbital, whereas anti-aromatic compound don't have electron in their bonding molecular orbital, whereas it has in their anti-bonding molecular orbital. Hope you understood all of this. Okay, so we'll start with the questions now. Let me just move it. Turn off here. Okay. And actually Huckel's rule is not followed when it comes to, there are some changes in Huckel rule we do when it comes to polycyclic compound. A lot of teachers won't even teach you this, but yeah, I'll teach you this either in this video or the next video, where we'll be completing all of that content. Okay, so yeah, and also we'll talk about quasi-aromatic compound and a lot more things. So yeah, this you have to tell whether this is aromatic, anti-aromatic, or non-aromatic. So this compound right in front of you, what we have to do, first few questions I'll do, then we'll do it together. Okay, we have to do is the 2 pi electron, and as I already told you, negative charge is also considered as lone pair electrons or 2 electrons. So it has total of 6 electrons, and as we remember, aromatic have 6, 10, 14, 18, and so on. And your anti-aromatic have 4, 8, 12, and so on. So this is aromatic. The next question we'll do is this question. Count the number of pi electron. So there are 4, right? So it is anti-aromatic. We'll do the next question as this. So yeah, let's go. To count the number of pi electron, 4. But it's not anti-aromatic, as this carbon right here is sp3 hybridized, because it has no pi electron, no pi bond. So if you counted sigma bond as when we draw the bond structure like this, we hide the hydrogens. So there are 2 hydrogens and 2 single bonds. So it has 4 bonds, which means it is sp3 hybridized. So this compound right here is non-aromatic. I hope you're getting it till now. We'll level up the question very soon. Okay? And the next question you get is this compound. Okay, so this compound right here with plus sign right here, so this is what? Aromatic, 2 electrons, right? Aromatic. The next question we'll do is this compound. This is one of the special case, so we are going to get into our special cases now. So what will you think what it is? By your normal, we can say that if you check correctly, then we also can actually do this, that as oxygen is more electronegative right here, the electron will go here as negative and form a positive here, negative, and form a positive here, and if you count that, then it comes to be aromatic. Okay, otherwise you might not think that way, but you have to consider those facts. Okay, and this is also aromatic if it has a hydrogen on top, because the hydrogen can leave. I'll talk about this. Actually, this forms in a special case which we'll talk about later on, okay, in some other lecture of organic chemistry, general organic chemistry. And how about this compound? Just check this out. I'll give you 10 seconds to do that. Yeah, this compound, just pause the video and write it down. What do you think? This compound has sp3 right here. Okay, so you will think it is non-aromatic, but the issue happens here is this is the keto form. Basically this compound will tautomerize and become anti-aromatic. Okay, so here tautomerization occurs. We'll talk about isomers in tautomerization. So this is the keto form, and it gets changed to the enol form. Okay, so we'll talk about tautomerization later on, although it can be or it cannot be, depends on the percentage of keto or enol form in our tautomerization, although it will have more of your keto form because a non-aromatic compounds are more stable, right? We'll talk about that. That is why when this tautomerization occurs, this one is not that stable. So that is why you will find more percentage of this in the tautomerization product. Okay. And another type of question which comes on this topic actually is your direction of dipole moment. They will ask you the direction of dipole moment. Okay, so these questions are really simple. I'll give you a few examples and then we'll move ahead. So they'll give you a figure like this and ask you the direction of dipole moment. So as you can see, this one right here, we'll have to shift it. So depending on which compound we need to make aromatic, depending on that we have to do it. So this time the electron will go down and it will have positive and this will have negative. So this will have 6 electrons, so it is aromatic too, and this will have 2, so it is aromatic. So to make both of them aromatic, what this charges should be applied, right? Which means the direction of our dipole moment you can predict right now after getting negative and positive charge, as dipole moment flows from positive to negative or negative to positive. I don't really remember right now completely, but yeah, I hope you understood how to do such questions, right? The next question is this is really important question. This is also called as pyridine. You'll get this name a lot across yourself, so just hang in with it. What do you think? Is it aromatic, non-aromatic, or what? Or actually the case here happens is you might think that this has 2, 4, 6, 8 electrons, right? Your anti-aromatic. but actually pyridine is aromatic. The issue is, I already talked with you about you can check this out in the first lecture of resonance, that we talked about localized and non-localized lone pair electron. And usually the lone pair electron which participates in your bond formation or in resonance are delocalized, and we don't count them while hybridization, but we count only localized lone pair. And in this case, this lone pair is localized, so you have to remember this. I'll give you this concept why this is localized. So if a lone pair electron or negative charge or a positive charge is directly attached to a double bond. One second. Is directly attached to a double bond. Then it won't take part in resonance. It won't take part in resonance. I'll tell you why too. Part in resonance. Why would it not take part in resonance? Well, let's figure that out. It won't take part in resonance, as you can see. If we create a resonating structure with this, right? What will happen is nitrogen will have double bond both sides, right? And it will be sp hybridized. Sp hybridized tend to be in a straight line, not in a circular way. That is why while we were doing Huckel's rule or aromaticity, we specifically said that it should be sp2 hybridized, because sp hybridized should be linear, and for aromatic compound it should be cyclic, right? So because of it being linear, we cannot put this into the resonance. So if we don't count this one, then it just have 2, 4, 6 electrons, so it's aromatic. Hope you understood it, right? Quite easy. Let's go ahead with our next one. Okay, and let's go with this case. Oxygen. This is also known as furan, F-U-R-A-N. That was pyridine, P-Y-R-I-D-I-N-E. Okay, so in this section, as we have learned that this furan, this will take part in resonance, right? This is delocalized. Why? Because it's not directly attached to any double bond, so it has total 6 electrons, so aromatic. Okay, hope you understood all of this. And another way, that example of that one, if such an example comes, then this positive charge won't take part in resonance. So here the carbocation is not resonance stabilized, so it's easy to react to it, right? Because it's not stable, and anything which is not stable want to get stable, so it's easy to react. But on the other hand, if we have such thing, then it's not that easy to react, because this positive charge is a bit more stable due to resonance. Okay, so this is resonance stabilized, but this is not. Okay, write it down if you want to in your notes. Okay, so we have seen furan. Next on, let's see what is called thiophene. The thiophene is literally similar as furan. Remember these names. These are some of the common names that you should remember. Okay, and then we come to another case which has such questions. If it comes, I have talked about all of these questions a lot before. If such questions come, we have to displace the charge, and then you have to see. Okay, it has 6 electrons after that. There is another case. 2, 4, 6, 7, 8, 9, 10. Okay. So we'll see some cases of anilines. Okay, and we'll check out. Firstly, let's check out what is quasi-aromatic compounds. I have my notes with me, so I don't miss any other topic that might be important for you. And as far as now, we have talked about the tautomer question, dipole questions, and those were some of the most important questions. So quasi-aromatic compounds, aromatic compound where positive or negative charge is completely dispersed around the ring. So if you see this, then here the positive charge is completely dispersed. That is why when we drew that with hydrogen, we removed the hydrogen because this was forming a quasi-aromatic compound, and quasi-aromatic compound are much more stable than normal aromatic compound, as you can also depict it like this, okay? As the negative charge is completely delocalized over the ring and it has higher dipole moment, higher dipole moment, and it is crystalline solid and soluble in water, okay? You won't find these concepts, I don't think anywhere. You might find it some places, but yeah, those are in some very good places, I would say. So yeah, next what we are going to do is, you remember Huckel's rule, we have done all the single ring question, all of those things, and we have also done a lot more questions. And what if you get some question like this, okay? Let's go with this. So what do you think it is? Is it aromatic or not? So you might say this is also known as C10H10. It should be aromatic, right? It has total of 2, 4, 6 as we calculate the pi, and lone pair 2, 4, 6, 7, 8, 9, 10. 10 electrons. 10 electrons, aromatic, but it is not aromatic. The issue happens here is this alpha hydrogen, and this hydrogen gets steric hindrance, due to which its structure, I'm talking about some exceptions, okay? Let's remember exceptions to our theory. Its structure will become non-planar, which will lead it to become non-aromatic, okay? Easy. Next, tell me about this question. So 2, 4, 6 aromatic, right? These are quite easy, right? 4, 6, 8. Okay, and there is another exception that you must know, your second exception. You have to remember these exceptions, and there are reasons for it. It's not like they're just some random exception, but you should remember with the reason. It's better. It should be anti-aromatic, right? But it becomes non-planar, and it has a structure. If you draw the real structure of it, it would look like something like this. Okay. So what happens is it becomes non-planar, as all the atoms are sp2 hybridized here, and there is a lot of angle strain due to 120 degree. Okay, so this is our second exception. And then I wanted to tell you about Huckel's rule, or I'll say changed Huckel's rule for your polycyclic compounds which have more than one cycle. So such as consider this case. It has a lot of cycles, right? Consider this case right in front of you. What do you think it should be? If you count all of the structure, then you'll find out 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, which means it should be anti-aromatic, right? It's a multiple of 4. But what happens is, like, whenever you have polycyclic compound, remember you have to only count the pi electron or negative charge on the peripherals. So this one will not be considered. So it will have 14 electrons, which will lead it to be aromatic. So it's not an exception. Those two are exceptions which we learned earlier. But these are all our real theory. So in polycyclic compound, you just have to calculate, you just have to see the peripheral, okay? You just have to see the peripheral of it, not any other way. So I'll give you another example from the one of the last concepts. So yeah, let's go with this. I've talked about a lot of theory. Let's discuss about them after we complete a bit more. Okay, what about this one? So here this one is delocalized, but this one isn't, because it is attached directly to a double bond, so it won't take part in resonance, so we'll only have 6, so which means it is aromatic. Okay, quite easy. The structure that we talked about, the compound which have alternate single and double bond, which having general formula to be CnH10 is also known as aniline. I don't think it's required, so yeah, but yeah, you should remember that these compounds which have alternate and this structure like C10H10 is called aniline. Okay, if we keep two methyl groups too, then also it will have steric hindrance and it will lead to non-aromatic. Okay, these are anilines because they have structure, they have formula of CnHn. Okay, and n is greater than or equal to 10. Okay, and you can also find, so aniline have a special property that aniline have alternate double bond, so it will have alternate single and double bond, so you don't need to, such as you also know one common aniline, which is 6-aniline, which is also known as your benzene, right? Benzene is a 6-aniline, alternate double and single bonds, C6H6, CnHn. And if an aniline have negative charge, then you can calculate the number of pi electrons directly by subtracting the subtracting the n, which is right here, this n, CnHn, and minus the charge. Okay, so if I know that this C4H4 is an aniline, and I want to check whether this one is aromatic, anti-aromatic, or non-aromatic, what I can do is to calculate number of pi electron, I'll just make 4 minus of minus 2, so it will lead to 6, which is aromatic. Hope you understood it. This formula is basically, you can draw a 4-1, but what if I give you something like this, C24H24 plus 6, and how are you going to do it? So we have to use this formula in such anilines. These are all advanced concepts, nobody will ask you in boards, and not even sometimes in some of competitive exam, but yeah, for competitive exam it's really, really important. There is another type of question on aromaticity. Just hang on with me, actually I want to complete aromaticity right here and resonance energy. So there are another type of question that they'll ask you whether this reaction will take place or not. Okay, such as I'll give you some more potassium or some other metal. Okay, it's easy, it's just a type of question on aromaticity, so I wanted to discuss about it. So whether it will react or not, so it will not react. Why? Potassium has always a positive charge, so what happens, it will form a negative charge here, right? When it attack here, it should have negative charge right here. Only this electron can form a bond, right? You can only replace this sp3 hybridized carbon's electron, because other hydrogens, you can only take out this hydrogen, and if you remove that hydrogen, this will form this, which is anti-aromatic, and a compound would always like to get to stability, not instability, right? So because it's more stable on the LHS, so it will stay there. Same in this case, if we take out an electron from here, which means giving it a negative charge, a hydrogen, which will give it 6, so this reaction will take place and form this compound right in front of you. So I hope you understood how you can know whether the reaction will take place or not by removing an hydrogen or giving just a negative charge. You can check out whether this reaction will take place or not. Such as, I'll give you another example of this question, the level up version of this. So they might also give you this. So usually AgNO3, usually what should happen is NO3 will displace this, right, this chlorine. So should it displace the chlorine or not? So if it displaces the chlorine, it will form a positive compound right there, and NO3 will attach with it. So and as you remember, this is aromatic and also quasi-aromatic, which is much more stable, so it will take place. Okay, similar way, let's give you another one. These are all really good examples, you won't find in a lot of books, and Yeah, book recommendations. If you want to ask from me, then I'll recommend you either you should try putting up questions from MS Chauhan or GR Bartla. I think there's one book named GR Bartla. I use that personally, but yeah, it doesn't matter until you do a lot of. Actually, if you remember all the concepts, then you just need to remember how to apply them. In chemistry, it's not like maths that you should do a lot and lot of practice. You need to remember concepts, and alongside, you need to remember when they are applied. You need to remember some few exceptions, which are not really an exception, but yeah. And so also for so yeah, you need to just hang in with one book. You don't need to go for 10 books. Just do questions regularly, just to remember the concepts and how it can be applied. Okay, so yeah, it will form this, which is again really stable. So yeah, it's gonna happen. So this reaction will take place. Next on, we'll go on to resonance energy, concept of resonance energy. Concept of resonance energy. This is a small concept. This will end our resonance and aromaticity section, and then we'll maybe start with the inductive effect in the next section and various other effects, where a lot of student gets confused with a lot of things. But I'm sure even I was confused when it was my time, but I'm sure what I've prepared right in front of you, you will never get confused with any of the questions. So yeah, if you have a compound like this in front of you, okay, and they'll ask you which one have more resonance energy. So resonance energy is basically the difference between resonance hybrid structures and most stable resonating structure. So it's the resonance energy is the concept of resonance energy is the difference between, if you want to write down, is the difference between the energy of resonance hybrid structure and the most stable resonating structure. So as you remember how to check this out, so there are further steps that you need to do. Firstly, we'll start with step 1 is, as I have already done in stability of similar resonating structures, so somehow it will be similar to that. Aromatic compound is greater than non-aromatic, right? Non-aromatic greater than anti-aromatic. Remember this, right? And then if this is all matching, then you go to equivalent resonating structure. We have talked about this in the last video about equivalent resonating structure and what are non-equivalent resonating structure. So equivalent resonating structure will always have more stability than non. Okay, we talked about it, and after that we'll see which has more resonating structure. So number of resonating structure, if those things are matching, resonating structures, and if that is also matching, then we'll go to our step 4, which will finalize it. Is molecule ion gives stable resonating structure, or molecule or ion whether it gives a stable resonating structure or not. So we'll see the stability of resonating structure too. Okay, so let's do some example on this to understand this better. We have already done how CO3 2- is more stable than COH, right? And we have about equivalent and non-equivalent, and then we have done aromatic compound related stability. So we'll go on with the big questions such as this. So they might even ask you that which one of these is more stable. So now both of them are aromatic, and this one is, we talked that this one was quasi-aromatic, so it is really stable. At the same time, this one is also quasi-aromatic, as the positive charge is dispersed over the whole cycle. So we can also make it like this, and then make a dotted structure all over here. So it has more dispersion, so it is more stable. Okay. Similar way you can compare. This is known as pyrrole. So what all we have learned today: furan, thiophene, pyridine, and pyrrole finally. Okay, so pyrrole, and if we see pyrrole and at the same time compare it with furan, which is oxygen. Okay, they have same structure, right? So if we compare both of them, then pyrrole will be more stable. Now why would pyrrole be more stable? This is known as pyrrole. Pyrrole will be more stable because for this electron to go into resonance, it's like if you are poor, okay, so if you are poor or if you are less powerful, it's easier for you to give anything, right, than if you are more powerful. So oxygen is more electronegative, so it will keep those lone pair with itself more. So the extent of resonance is already there, like it's aromatic resonance and everything is there, but still this one, oxygen is not letting go your lone pair very easily, whereas nitrogen is letting it go very easily. Okay, let's do another example. On resonance energy, the lecture is going a bit long, but I wanted to get done with resonance energy so we can move forward. We have NH2. Okay, my mouse is even not working that well. Then we have benzene, which have alternate, okay. Then we have benzene OH, phenol, and then we have methoxybenzene, which is OCO3. Yeah, if you are confused with the naming, I'll teach you that, no issues, okay. And a lot of people get confused between both of these, and we're going to demystify all of these, so stay connected. First one, who is the most stable? So the most stable one is our A, okay, and the least stable right here is, no, we are talking about resonance energy, and we have to see stability in resonance energy, okay. So if you see for resonance energy, the ion which will give more resonating structure will be more stable, right, as we already talked about this, right? We have talked about it, that which gives more resonating structure will be more stable, and NH2 will have more resonating structure than benzene. Even both of these will have resonating structure than benzene, so the last one will be benzene, right? So last one will be our B. But now the issue comes between C and D, how to check which one is better. Or so again, here we have one OCH3 and one OH. What we need is these lone pair to just go really easily, okay. So but at the same time, here carbon is more, the electronegativity with difference between here, this and this. Oxygen is usually 3.5 and this is 2.1. Here the electronegativity difference will be higher, right, and here the electronegativity difference is lower. I'm giving you facts, but you can literally remember that carbon is more electronegative than hydrogen, right? So the electronegativity difference is lower, due to which this causes there's negative charge more towards it, and this does not. So this negative charge can easily disperse into our cycle. So C is more stable than D, okay. At the same time, a lot of people have asked me if OH or OR, which one is better leaving group. So we see the same thing. So to just make it leave, okay, and you will have a negative charge on both of these, as that will take negative. And now check out which one of these negative charge will be more stable. And as you can see, the R1 will be more stable, as R will try to take this negative charge on itself, due to which the negative charge will become less intense and it will be more stable. Similar way, okay. Let's go to some or more equations. I'll give you a lot of questions, you'll have fun. Let's check it out. Which one has more resonating energy, or we can have 3, 4, or so C, B, A. As the number of cycle increase, resonance increase, so resonating energy increase. Okay, easy peasy, right? At the same time, so we have learned about this, but at the same time, if we see resonance energy per benzene, if the question has asked you that which one has more resonance energy per benzene, then the order will be, per benzene, the order will be opposite, okay. It will be A, B, C. Let's do one more questions and we will be done with it, okay. So yeah, the last question is the concept here is the resonance energy of 2 fused ring is higher than 1 benzene ring but less than 1 pure benzene, okay. at individual. So last question you have is, let's just get the clear frame and let's just write it down clearly. Last question you have is this: benzene, second is your secondary benzene, so it will have CH and another benzene. Okay, here I'll write it as BN. Okay, and then you have C as this option, so we are comparing two different types of benzene. Then you have a tertiary benzene. I'll just write BN on the side. Okay, BN means this ring, C, D. Then you have E as triple benzene that we made earlier. Which one will have more resonance energy? So the order of resonance energy here is D, then E. Firstly, the one which will have more benzenes will be more aromatic. So this one has 3, this one has 3. These two have 2, and this one has 1. So this one will be the last, right? A will be the last. And we have to figure out between these two and these two. So you have to remember that 2 fuse ring benzene, overall your overall resonance energy decrease. Okay, so this is some of like examples that you need to remember. Okay, and these are some of the concepts which nobody will ask you in CBSE. CBSE, if you want to just learn about CBSE, then and you need to know. So some concepts, the resonance energy is not part of it, and if you want to know only the concept, then the Huckel's rule and aromaticity, non-aromaticity, anti-aromaticity, and difference between them is part of CBSE. So you should remember that. Although not these questions, not these tough questions that we have done, and not the concept of allolene or change Huckel's rule or your exceptions. None of these exceptions or quasi-aromatic compound is part of your board or anything. So if you are preparing for a competitive exam, then only all of this is part of. And if you are if you're learning for just knowledge, then yeah, only till this it's important. I hope you understood the overall concept, and this video went quite a lot long because I had to teach a lot of things and I had to make you do a lot of questions so you don't get confused about any of these topics. Next on, we are going to learn about electron displacement through inductive effect, mesomeric effect, hyperconjugation, and electromagnetic effect. I'll have a lot of tricks in my sleeves for all of them, and alongside we are going to have fun along with it, and we're going to do some advanced questions too. But yeah, you need to suggest me one thing before leaving is, should I make those type of question in another video, or should I just include them with our normal section what we are doing? So if you want such as like normal and advanced concepts indifferently, then I can do that too. Take care, have fun, enjoy learning, and I hope you have a great day. I'll see you in the next video.